Good morning. Rahul welcomes you. Today we are going to talk on topic nuclear fission. What is fission? Nuclear fission is a process in which the nucleus of atom splits into two or more smaller nuclei along with release of energy. This process is opposite to nuclear fusion, where two smaller nuclei combine to form larger one. In a fission reaction, a heavy nucleus, often that isotope of uranium or plutonium, absorbs neutron and becomes unstable and then splits into two or more higher lighter nuclei, releasing a significant amount of energy. Additionally, several neutrons are usually emitted during the process. These neutrons can go on induce further fission reactions in nearby nuclei, creating a self-sustaining chain reaction. Fission reactions are basis for nuclear power plants and nuclear weapons. In nuclear power plants, controlled fission reactions are used to generate heat, which is often used to produce steam and drive turbines that generate electricity. In nuclear weapons, an uncontrollable chain reaction is triggered, resulting in powerful explosion. It's worth noting that there are various isotopes and conditions that can influence the characteristic of a fission reaction, and they are crucial factors in design of and operation of nuclear reactors and weapons. How nuclear fission takes place? Nuclear fission is a process that takes place in the nucleus of atom, and it involves the splitting of nucleus into two or more smaller nuclei. Here, a basic outline of how nuclear fission occurs. Initiation. The process begins with absorption of neutron by nucleus of heavy atom, typically uranium-235 or plutonium-239. These isotopes are preferred for fission reaction because they are more likely to undergo fission when they absorb a neutron. Nucleus becomes unstable. When a neutron is absorbed, the nucleus of atom becomes unstable. The extra neutron can cause nucleus to become highly excited, splitting of nucleus. As a result of instability, the nucleus splits into two or more smaller nuclei. This is actual fission reaction. In addition to smaller nuclei, several neutrons are also released during the process. Release of energy. The key factor of nuclear fission is the release of significant amount of energy. This energy is released in the form of kinetic energy of the fission fragments, the smaller nuclei, as well as the kinetic energy of neutron that is emitted. Neutron propagation. The neutrons released in the fission reaction can go on to induce fission in other nearby nuclei, creating a chain reaction. If the chain reaction is controlled, it can be harnessed for useful purposes, such as generating electricity in nuclear power plants. The chain reaction is carefully controlled in nuclear power plants to ensure a steady release of energy and prevent uncontrolled reaction that could lead to a nuclear explosion. In contrast, nuclear weapons are designed to allow an uncontrolled chain reaction, resulting in powerful explosion. How fission can be utilized by people? Nuclear fission has several important applications that are harnessed for various purposes, primarily in the generation of electricity, the production of isotopes for medical industries, and research purposes. Here are some ways in which fission is utilized by people. Nuclear power generation. One of the primary use of nuclear fission is in generation of electricity in nuclear power plants. Fission reactions release large amount of energy, which is used to heat water, produce steam, and drive turbines that generate electricity. Nuclear power plants provide a significant portion of the world's electricity and are known for their high energy density and low carbon emissions compared to traditional fossil fuel-based power plants. Isotope production. Nuclear fission is used to produce specific isotopes for medical, industrial, and research applications. For example, the production of radioisotopes is crucial in medicine for diagnostic imaging, cancer treatment, and sterilization of medical equipment. Unfortunately, nuclear fission has also been utilized for destructive purposes in the form of nuclear weapons. These weapons use uncontrolled nuclear fission reaction to release an immense amount of energy, resulting in a powerful explosion. Nuclear research. Fission reactions are used in scientific research to study nuclear physics and properties of material. Research reactors are employed for various experiments, including neutron scattered radiograph and study of nuclear reaction. Space exploration. Nuclear fission has been considered for space exploration, particularly for providing power to space aircraft on long-duration missions. Nuclear research can generate electricity for spacecraft over extended periods, where solar power might be less practical due to distance of sun or for other environmental factors. It is important to note that while nuclear fission has various benefits applications, there are also significant concerns related to nuclear safety. Radioactive wastes, disposal and proliferation of nuclear weapons. The responsible and safe management of nuclear technology is essential to initiate these risks and ensure that the benefits of nuclear fission are realized without adverse consequences. When the basic material for fission is found, the primary metal used is uranium-235, which is found in nature. However, natural uranium is mostly composed of uranium-238, which is not as readily fissionable. Therefore, the process of obtaining the basic material for fission involves extracting the enriched uranium-235 from natural uranium. Here is an overview of process. Mining. The first step is in mining uranium ore. Uranium is found in various types of rocks and can be extracted through mining operation. Milling. The mined uranium ore is then processed to extract. This involves crushing the ore and extracting uranium in the form of uranium oxide. Conversion. The extracted uranium oxide is converted into more reactive form, typically uranium hexafluoride UF6, which can undergo enrichment. Natural enriched uranium contains about 0.7% uranium-235 and 99.3 uranium-238. Enrichment is the process of increasing the concentration of uranium-235, making it suitable for use in nuclear reactors or weapons. There are various methods of enrichment, including gas diffusion, gas centrifugation, and laser isotope separation. Fuel fabrication. Enriched uranium is then converted into fuel for nuclear reactors. In this form, it can be used for nuclear power plants to generate electricity. It is important to note that another fissile metal, plutonium-239, can also be used. Plutonium-239 is found in nature in significant quantities but can produce artificially in breeder reactors where uranium-238 absorbs neutron and transforms into plutonium-239. Both uranium-235 and plutonium-239 can serve as basic material for nuclear fission reaction in power plants or weapons, and they are obtained through combination of mining process and enrichment process. The management and control of these materials are essential to prevent their misuse for nuclear weapon proliferation. Where and how nuclear fission generates electricity. Nuclear fission generates electricity in nuclear power plants through a controlled process that harnesses heat produced by a fission reaction. Here, a simplified overview of how nuclear fission generates electricity. Fuel preparation. The process begins with the preparation of nuclear fuel. The most common fuel for fission is uranium-235, which is extracted from naturally occurring uranium ore and enriched to increase the proportion of uranium-235. Fission reaction. Enriched uranium fuel is placed in reactor core where a uranium-235 nucleus absorbs a neutron. It becomes unstable and undergoes nuclear fission, splitting into two or more smaller nuclei. This process releases a significant amount of energy in the form of heat. Controlled chain reaction. The fission reactions can also release additional neutrons, which can go to induce further fission reaction in nearby uranium-235 nuclei, creating a chain reaction. Controlled rods made of material that absorbs neutrons are used to regulate and control the rate of chain reaction. Heat generation. The heat generated by the fission reaction is absorbed by a coolant circulating through the reactor core. The most common coolant is water, but other substances like heavy water or liquid sodium can also be used. Steam production. The heat transferred to the coolant is then used to produce steam by boiling water. This steam is at high pressure and is used to turn a turbine. Turbine rotation. The high pressure steam causes the turbine blades to rotate. Electricity generation. The rotating turbine is connected to a generator and as it turns, it produces electricity. The generator converts the mechanical energy from the turbine into electrical energy. Cooling. After passing through the turbine, the steam is condensed back into water and water is then returned to the reactor core to absorb more heat, restarting the cycle. The process of converting nuclear fission heat into electricity is known as Rankine cycle, similar to cycle used in many conventional power plants. The key difference is that heat source in nuclear power plants, it comes from controlled nuclear fission reaction. Nuclear power plants provide a continuous and reliable source of electricity with low carbon emissions, making them important component of many countries' energy portfolios. However, the management of nuclear materials and safe operation of nuclear power plants are crucial to prevent accidents and ensure responsible use of nuclear energy. What essential things are required for establishing a nuclear power plant? Establishing a nuclear power generation plant is a complex and highly regulated process that involves various technical, economical, and regulatory considerations. Here are some essential factors and requirements for establishing a nuclear power plant. Site selection. Identify a suitable site that meets safety and environmental criteria. Proximity to a reliable water source for cooling purpose. Consideration of seismic and geological factors to ensure stability. Regulatory approval. Obtaining regulatory approval from the relevant government agencies, complying with national and international nuclear safety standards, demonstrating adherence to environmental regulations. Safety measures. Implementing robust safety systems to prevent accidents and mitigate their consequences. Emergency preparedness and response plans in case of unforeseen events. Nuclear fuel supply. Securing a reliable supply of nuclear fuel, typically enriched uranium or mixed oxide MOX fuel. Establishing agreement for the purchase of transport of nuclear fuel. Cooling system. Designing and implementing efficient cooling system to manage the heat generated during the nuclear fission reaction. Reactor design. Choosing a suitable reactor design based on factors like safety, efficient, and cost. Ensuring that design meets regulatory requirements and standards. Engineering and construction. Developing detailed engineering plans for the construction of power plant. Engaging experienced contractors with expertise in nuclear facility construction. Financing. Securing the necessary funding for the construction and operation of the nuclear power plant. Obtaining financial support, loans, or partnership with private or public entities. Workforce and training. Developing a skilled and qualified workforce with expertise in nuclear technology. Providing ongoing training and education for plant personnel. Waste management. Implementing plans for safe storage and disposal of nuclear waste generated by the power plant. Complying with regulations regarding the handling and disposal of radioactive materials. Grid connection. Establishing connection to the electrical grid to distribute the generated electricity. Power outreach and acceptance. Conducting public outreach programs to inform and engage local community. Addressing concerns and ensuring public acceptance of the nuclear power plant. Security measures. Implementing security measures to protect the facility from unauthorized access and potential sabotage. International cooperation. Collaboration with international organizations and agencies to ensure compliance with global nuclear safety and non-proliferation standards. The establishment of nuclear power plant requires careful planning, adherence to strict safety standards, and compliance with regulatory frameworks. It involves a significant investment and a long-term commitment to safe and responsible operation of facility. What are advantages and disadvantages of nuclear power generation plant? Nuclear power generation has both advantages and disadvantages. Nuclear power generation has both advantages and disadvantages, and assessment of these factors often depends on various perspectives, including environmental impact and economic consideration. Here are an overview of the key advantages and disadvantages of nuclear power. Advantages: low greenhouse gas emissions. Nuclear power plants produce electricity with low carbon dioxide emissions, contributing to the reduction of greenhouse gases and addressing climate change concerns. High energy density. Nuclear fuel has a very high energy density, meaning that a small amount of fuel can produce a large amount of electricity over an extended period. Reliable power source. Nuclear power provides a stable and reliable source of electricity capable of producing a continuous output at a relatively constant level, unlike some renewable sources like wind or solar. Base load power. Nuclear power is well suited for providing base load power, which is the constant minimum amount of electricity needed to meet their basic demand. Energy security. Nuclear power can contribute to energy security by diversifying the energy mix and reducing dependence on fossil fuels. Long operation life. Nuclear power plants can have long operational lifespan, often exceeding 40 years, which can contribute to stable and predictable energy supplies. Reduce dependence on fossil fuels. Nuclear power helps reduce dependence on fossil fuels for electricity generation, contributing to energy diversification. Disadvantages. Nuclear accidents. The risk of nuclear accidents, although low, can have severe consequences on human health and environment, as demonstrated by events like Chernobyl and Fukushima. Radioactive waste. Nuclear power plant radioactive waste that needs to be stored and managed for thousands of years. The long-term disposal of nuclear waste remains a significant challenge. Nuclear proliferation. The spread of nuclear technology for power generation can raise concerns over the potential misuse of nuclear material for the development of nuclear weapons. High initial cost. The construction of nuclear power plant involves a high initial capacity cost. Delays and cost overruns are common in construction of nuclear facilities. Limited fuel supply. The availability of uranium, the primary fuel for nuclear reactors, is finite. However, technological advancements such as BD reactors or alternative fuel cycles could potentially extend the supply. Public perception and acceptance. Public concerns about the safety of nuclear power, especially after major accidents, can lead to opposition and challenging in gaining public acceptance for the nuclear projects. Security risk. Nuclear facilities pose security risks, and there is a need for stringent measures to prevent unauthorized access, theft of nuclear material, or sabotage. Balancing the advantages and disadvantages of nuclear power requires careful consideration of safety measures, waste management, strategies, regulatory frameworks, and public engagement. Ongoing technological advancement and research aim to address some of the challenges associated with the nuclear power generation. Which power generation technique is better than nuclear power plant? The assessment of which power generation technique is better depends on various factors including geographical location, energy requirement, environmental consideration, safety concerns, and economic consideration. Each power plant generation method has its advantages and disadvantages. Here are a few alternatives often considered in comparison to nuclear plant power. Renewable energy source. Solar power. Solar energy is abundant and environmentally friendly. Solar panels convert sunlight into heat into electricity, and advancement in technology have made solar power increasingly cost effective. However, solar power is intermittent and independent of weather conditions. Wind power. Wind turbines generate electricity from kinetic energy of the wind. Wind power is also renewable and has a low environmental impact compared to fossil fuel and nuclear power. Like solar, wind power is intermittent. Hydropower. Hydropower harnesses the energy of flowing of water to generate electricity. It is reliable and established technology and low greenhouse gas emission. However, Large-scale hydropower projects can have environmental and social impacts. Natural gas power plants. Natural gas power plants burn natural gas to produce electricity. Natural gas is relatively abundant and produces fewer carbon emissions than coal. However, it is still a fossil and contributes to greenhouse gas emission. Geothermal power. Geothermal power harnesses heat from Earth's interior to generate electricity. It is a reliable and continuous source of energy, but it is location specific and not universally acceptable. Energy storage systems. The advantage of energy storage technologies such as batteries are making it possible to store energy generated from intermittent sources like solar and wind. This helps address the issue of variability and provides a more stable power supply. These aim to address concerns or challenges associated with traditional nuclear power, such as safety, waste, and management and cost. The best power generation technique depends on a specific requirement of constraints over the given situation. For example, the country with abundant wind might benefit from wind power. Additionally, a combination of different energy sources known as diversified mix is often recommended to balance the strengths and weakness of individual technologies. It is important to consider a holistic approach that includes environmental impact, safety, reliability, and economic viability when evaluating power generation options.